Historic discovery, K2-18b reveals potential biosignatures paving the way for future exoplanet research.
Introduction.
In a groundbreaking development that has captured the attention of the scientific community, recent investigations into the exoplanet K2-18b have unveiled potential biosignatures in its atmosphere, suggesting the possibility of extraterrestrial life. This exoplanet, located approximately 120 light-years away in the constellation Leo, has been the subject of intense scrutiny since its discovery in 2015. Utilizing the advanced capabilities of the James Webb Space Telescope, JWST researchers have made significant strides in understanding the atmospheric composition of K2-18b, including the detection of carbon-bearing molecules such as methane and carbon dioxide, along with a tentative identification of dimethyl sulfide DMS.
Background on K2-18b.
K2-18b is classified as a sub-Neptune exoplanet weighing approximately 8.6 times the mass of Earth.
It orbits a cooler dwarf star and resides within the star's habitable zone,
where conditions may permit the presence of liquid water, a critical factor for life as we know it. Initial observations from the Hubble Space Telescope in 2019 revealed water vapor in K2-18b's atmosphere, which piqued interest in its potential to harbor life. The latest findings from JWST further support the hypothesis that K2-18b may be categorized as a Hycean exoplanet characterized by a hydrogen-rich atmosphere and a surface covered by oceans.
Key findings from the JWST observations. The JWST observations have yielded several critical insights into K2-18b's atmospheric composition.
The following points encapsulate the major discoveries. 1. Detection of methane and carbon dioxide. The analysis revealed a substantial presence of methane and carbon dioxide in K2-18b's atmosphere.
Notably, the absence of ammonia suggests the likelihood of an underlying ocean of water aligning with the characteristics of Hycean exoplanets. 2. Tentative detection of dimethyl sulfide DMS. The identification of DMS is particularly intriguing,
as this compound is primarily associated with biological processes on Earth predominantly produced by marine phytoplankton. However, the detection remains tentative and is subject to ongoing scrutiny, as DMS can also form through non-biological processes. 3. Robustness of data. The JWST's advanced spectroscopic capabilities allowed researchers to gather detailed atmospheric data from only 2 transits of K2-18b, showcasing the telescope's ability to glean significant information rapidly. This precision surpasses what was achievable with previous telescopes such as the Hubble Space Telescope.
The analytical process.
The process of analyzing K2-18b's atmosphere involves a technique called transmission spectroscopy. This method entails measuring the starlight that passes through the exoplanet's atmosphere during a transit. As the light traverses, the atmosphere's specific wavelengths are absorbed by various molecules, creating a unique spectral signature that astronomers can decode to determine the atmospheric composition. This technique presents challenges due to the overwhelming brightness of the host star, which can obscure the faint signals from the exoplanet.
Caution in interpretation.
Despite the promising findings, the scientific community remains cautious in its interpretation of the data. Notable astronomers including Niku Madhusudhan, the lead author of the study, have emphasized the preliminary nature of these results.
The identification of DMS, while exciting, requires further validation through additional observations.
Other experts such as astrobiologist Edward Schwieterman have called for careful consideration of the potential non-biological origins of DMS, highlighting the complexities involved in interpreting atmospheric data. Historical context of K2-18b research.
The timeline of research on K2-18b illustrates the evolution of our understanding of this intriguing exoplanet.
2015, K2-18b was first discovered by NASA's K2 mission,
marking its entry into the catalog of known exoplanets.
2019, the Hubble Space Telescope detected water vapor in the atmosphere, suggesting conditions favorable for liquid water.
September 2023, the JWST announced the detection of methane carbon dioxide and the tentative identification of DMS.
April 2024, plans for further investigations with the JWST aim to explore K2-18b's atmospheric conditions in greater detail. The debate among scientists.
The potential implications of these findings have sparked a lively debate within the scientific community.
While some researchers express excitement over the prospect of identifying extraterrestrial life, others caution against overinterpretation. Ian Whittaker, a prominent voice in the discourse, notes that although the indicators are suggestive, they do not constitute definitive proof of life. The complexity of atmospheric chemistry means that many factors could influence the presence of these molecules, making it essential to approach conclusions with a critical mindset. Future research directions. The next steps in the investigation of K2-18b involve the utilization of JWST's mid-infrared instrument MIRI spectrograph to further validate the findings and enhance our understanding of the planet's environmental conditions.
Ongoing observations will be crucial in determining the veracity of the DMS detection and exploring the broader implications for the search for life beyond Earth. Conclusion.
The discoveries surrounding K2-18b represent a significant milestone in the field of exoplanet research, highlighting the capabilities of state-of-the-art instruments like the JWST and the evolving methodologies used to study distant worlds. While the presence of potential biosignatures like DMS raises exciting possibilities for the existence of life beyond our planet, the scientific community must tread carefully, ensuring that interpretations are grounded in robust evidence.
As research continues,
K2-18b stands as a focal point for the ongoing quest to understand habitable environments in the universe and the nature of life beyond Earth. In the recent exploration of the exoplanet K2-18b, significant findings have emerged that point toward potential biosignatures in its atmosphere, drawing both excitement and skepticism from the scientific community. Here are some counterintuitive aspects of the information surrounding these discoveries. 1. Detection of dimethyl sulfide DMS. While DMS is typically associated with biological activity on Earth, its tentative detection on K2-18b is contentious.
Scientists have pointed out that DMS could also be formed through non-biological processes,
such as chemical reactions occurring on comets. This raises the question of whether the presence of DMS is a strong indication of life or merely a signal of extraterrestrial chemistry that does not involve biology. 2. Hydrogen-rich atmosphere and potential oceans. K2-18b's classification as a Hycean exoplanet suggests it could have a hydrogen-rich atmosphere and a water-covered surface. However, the planet's size, 8.6 times that of Earth, implies that it may also possess a thick mantle of high-pressure ice. This complexity leads to a paradox. While the conditions may seem conducive to liquid water and potentially life, the high pressure and temperature could render the oceans too hostile for life as we know it. 3. Caution in interpretation. Despite the presence of carbon-bearing molecules like methane and carbon dioxide, which are often seen as potential biosignatures, the absence of ammonia is used to support the hypothesis of a subsurface ocean. This counterintuitive interpretation underscores the difficulty in drawing definitive conclusions from atmospheric data. The interpretations are based on indirect evidence and complex modeling, which could lead to both false positives and negatives regarding the potential for life. 4. Spectroscopy challenges. The process of identifying atmospheric compositions via spectroscopy involves light from a star passing through the planet's atmosphere. This method is akin to looking through a tinted glass. The presence of multiple chemicals can obscure the signals of individual substances. This inherent complexity complicates the analysis and may lead to misleading conclusions about the atmospheric constituents. 5. Historical context of extraterrestrial life detection. The excitement surrounding K2-18b's findings echoes previous instances in astrobiology, such as the phosphine detection on Venus. which was later refuted. This historical context serves as a cautionary tale about jumping to conclusions based on preliminary data. It highlights the necessity for rigorous validation of findings before making claims about the existence of life. 6. Energy output in habitable zone. K2-18b orbits its host star at a distance that places it within the habitable zone, but the star itself has a power output much lower than that of the Sun. This creates a paradox where, despite being in the habitable zone, the lower energy output could lead to a planet that is not actually conducive to life, especially when factors such as cloud cover and surface reflectivity are considered. 7. Broader implications for astrobiology. The ongoing investigations into K2-18b challenge the traditional focus on smaller rocky planets as the primary targets for the search for extraterrestrial life. The findings suggest that larger Hycean worlds, which do not exist in our solar system, may also be viable candidates for hosting life, thereby expanding the criteria for what constitutes a habitable environment. In conclusion, K2-18b presents a fascinating case study in the search for extraterrestrial life, illustrating the complexity and nuance involved in interpreting potential biosignatures. The findings serve as a reminder of the need for careful analysis and validation, as well as an invitation to rethink existing paradigms in astrobiology. The recent investigation into the exoplanet K2-18b has unveiled potentially groundbreaking insights into the search for extraterrestrial life, particularly through the use of the James Webb Space Telescope JWST. While the findings are significant, several critical aspects are often overlooked or underappreciated in discussions surrounding K2-18b and its atmospheric analysis. Here are some of these overlooked elements and their significance. 1. The role of dimethyl sulfide DMS as a potential biosignature. One of the most intriguing findings from the JWST observations is the tentative detection of dimethyl sulfide DMS in the atmosphere of K2-18b. DMS is primarily produced by marine phytoplankton on Earth, making its presence a compelling indicator of biological activity. However, the detection of DMS is not straightforward and is contentious. Critics argue that DMS could also arise from non-biological processes such as those occurring in cometary environments. This ambiguity is significant because it highlights the challenges in interpreting potential biosignatures, emphasizing the need for caution in claiming the presence of life based solely on atmospheric compositions. Why it matters. Understanding the origin of DMS is crucial for astrobiology. It illustrates the limitations of current detection methods and the necessity for further observational data to confirm or refute its biological significance. The debate surrounding DMS serves as a reminder that the search for life must consider multiple hypotheses and interpretations rather than jumping to conclusions based on limited evidence. 2. The methodology of atmospheric analysis. The technique used to detect atmospheric constituents involves analyzing starlight that passes through K2-18b's atmosphere during transits. While this method has yielded promising results, it is fraught with challenges, including the potential for misinterpretation of the data due to overlapping spectral signatures from various chemicals. The complexity of separating the atmospheric signals from the star's own light means that the interpretation of results can be subjective and prone to error. Why it matters. The methodological limitations underscore the importance of developing more refined techniques for atmospheric analysis. As more exoplanets are studied, understanding the nuances of these methodologies will be critical in distinguishing between genuine biosignatures and false positives. This knowledge will shape future research priorities and funding in the field of exoplanetary science. 3. The concept of Hycean worlds. K2-18b is categorized as a potential Hycean world characterized by a hydrogen-rich atmosphere and possibly vast oceans. This classification expands the traditional focus of astrobiology, which has predominantly centered on smaller, rocky planets. The recognition of Hycean worlds as viable candidates for hosting life is significant because it suggests that habitability can take many forms, broadening the scope of where we might search for life in the universe. Why it matters. The Hycean model challenges preconceived notions about the conditions necessary for life and encourages scientists to explore diverse planetary environments. This shift in perspective could lead to the discovery of life in places previously thought inhospitable,
fundamentally altering our understanding of life's potential diversity.
4. The importance of continuous observation. The findings on K2-18b are preliminary and require validation through ongoing observations.
The scientific community is acutely aware that initial results must be corroborated by subsequent studies to build a robust case for the presence of biosignatures. Upcoming observations with JWST and other telescopes will be essential in refining our understanding of K2-18b's atmosphere. Why it matters. This emphasis on continuous observation highlights the iterative nature of scientific discovery. It serves as a reminder that extraordinary claims require extraordinary evidence and that the scientific process is inherently built on revising and refining hypotheses in light of new data. 5. The enthusiasm versus skepticism dichotomy. The excitement surrounding K2-18b's findings often contrasts with a more cautious skepticism expressed by parts of the scientific community. While some researchers advocate for the potential implications of the results, others stress the need for rigorous validation before concluding that extraterrestrial life exists on K2-18b. This dichotomy is significant as it reflects broader tensions within the field of astrobiology regarding how to interpret ambiguous evidence and the implications of such interpretations. Why it matters. This tension between enthusiasm and skepticism is essential in the scientific discourse surrounding exoplanets. It fosters a culture of rigorous debate and critical thinking, ensuring that claims regarding extraterrestrial life are substantiated and not based solely on wishful thinking. Balancing optimism with scientific rigor will ultimately lead to more credible and trustworthy conclusions in the search for life beyond Earth. 6. Potential implications for understanding Earth's formation. Studying K2-18b and similar exoplanets can provide valuable insights into the conditions that lead to planetary habitability, including the role of water and atmospheric composition. Understanding these factors may help scientists draw parallels with Earth's own history and formation, offering clues about how life might evolve in different environments. Why it matters. This connection between exoplanetary studies and Earth's geological and biological history emphasizes the broader relevance of such research. It could inform our understanding of Earth's past and guide our search for life on other planets, ultimately helping us understand our place in the universe. Conclusion. The investigation of K2-18b is a significant milestone in the search for extraterrestrial life, but it is essential to recognize the complexities and nuances that accompany these findings. The potential biosignatures, methodological challenges, and the broader implications for astrobiology all deserve careful consideration. Acknowledging these often overlooked aspects not only enriches the discourse surrounding K2-18b but also enhances our understanding of the search for life beyond Earth, ensuring that future research is grounded in scientific rigor and open-mindedness. As we continue to explore the cosmos, the lessons learned from K2-18b will undoubtedly shape our approach to the profound question of whether we are alone in the universe. Key points for in-depth analysis and discussion on K2-18b. 1. Potential biosignatures and their implications. The discovery of methane, carbon dioxide, and a tentative detection of dimethyl sulfide DMS in the atmosphere of the exoplanet K2-18b raises intriguing questions about the potential for life beyond Earth. DMS is particularly noteworthy as it is primarily produced by phytoplankton on Earth, suggesting a biological origin. While the presence of such molecules hints at possible biological activity, the scientific community remains cautious. The interpretation of these findings is complicated by the potential for non-biological processes to create similar chemical signatures. A thorough understanding of these biosignatures and their origins is essential for deciphering the conditions that might support extraterrestrial life. 2. Challenges in exoplanet atmospheric analysis. Analyzing the atmospheric composition of distant exoplanets like K2-18b presents significant scientific challenges.
The method used involves spectroscopy, where starlight passes through an exoplanet's atmosphere, allowing for the identification of chemical compounds based on their spectral signatures. This process, akin to looking through a glass filled with colored dyes, is subject to numerous variables, including the influence of the parent star's light and the presence of multiple overlapping atmospheric compounds. The complexity of this analysis highlights the need for advanced technologies and methodologies to improve the accuracy of exoplanet studies. As evidenced by the capabilities of the James Webb Space Telescope JWST compared to previous instruments like the Hubble Space Telescope. 3. Hycean worlds and their importance. K2-18b is categorized as a Hycean exoplanet, which is characterized by its hydrogen-rich atmosphere and potential water-covered surface. This classification is significant as it expands the traditional understanding of habitable environments beyond rocky planets akin to Earth. Hycean worlds may offer unique conditions conducive to life, potentially altering the criteria for habitability in astronomical research. The ongoing study of such planets could provide insights into the diversity of environments that might support life and encourage the exploration of broader atmospheric compositions in future exoplanet research. 4. Scientific caution in future research directions. Despite the excitement surrounding the findings related to K2-18b, the scientific community emphasizes caution in interpreting these results. The preliminary nature of the findings necessitates further validation through additional observations and studies. Upcoming JWST investigations are planned to probe deeper into K2-18b's atmospheric conditions, which may help confirm or refute the presence of DMS and other potential biosignatures. This ongoing research underscores the importance of rigorous scientific methodology in exoplanet exploration and the need to remain skeptical of early conclusions, ensuring that claims of extraterrestrial life are substantiated by robust evidence. Conclusion. The study of K2-18b serves as a pivotal moment in exoplanet research, highlighting both the potential for discovering extraterrestrial life and the complexities involved in such investigations. As research progresses, it will be crucial to maintain a balanced perspective that acknowledges the remarkable findings while also recognizing the need for careful analysis and validation. The outcomes of future studies on K2-18b could significantly enhance our understanding of life's potential in the universe and guide the methodologies employed in the search for habitable worlds beyond our solar system. 1. The detection of phosphine on Venus 2020. In September 2020, a group of astronomers announced the detection of phosphine gas pH3 in the atmosphere of Venus, which sparked widespread excitement and speculation about the possibility of life in the planet's upper atmosphere. Phosphine is a molecule that on Earth is primarily produced by anaerobic bacteria, leading to debates about whether its presence on Venus could indicate biological processes. The findings were based on data from the James Clerk Maxwell Telescope and the Atacama Large Millimeter/Sub-Millimeter Array. However, subsequent studies raised questions about the reliability of the phosphine detection and proposed alternative non-biological processes that could account for its presence. The controversy over phosphine on Venus highlights the challenges of interpreting atmospheric data and the importance of further investigation into potential biosignatures. 2. The Mars Methane Mystery 2003, present. The ongoing investigation into methane detection on Mars represents another significant case in the search for extraterrestrial life. Methane CH4 has been detected intermittently in the Martian atmosphere by several missions, including the Mars Curiosity rover and ESA's Mars Express. On Earth, methane is predominantly produced by biological sources, leading to speculation that its presence on Mars could suggest microbial life. However, measurements have shown that methane levels vary, raising questions about its origin and stability in the Martian atmosphere. Some scientists propose that geological processes such as serpentinization could also produce methane. The search for methane on Mars continues.
With missions like the Mars 2020 Perseverance rover aiming to provide further insights into the planet's potential for habitability. 3. The discovery of water on Europa 1996.
In 1996, data from NASA's Galileo spacecraft suggested the presence of a subsurface ocean beneath the icy crust of Europa, one of Jupiter's moons. This finding, combined with the moon's surface features, indicated that liquid water might exist, creating a potentially habitable environment for life. The discovery sparked interest in Europa as a target for astrobiological exploration. Subsequent missions, including the upcoming Europa Clipper mission, aim to investigate the moon's ice shell and subsurface ocean more closely. The presence of water, along with the potential for chemical interactions between the ocean and the moon's rocky mantle, raises exciting possibilities for the existence of life beyond Earth. This case underlines the importance of exploring celestial bodies in our solar system that may harbor conditions suitable for life. The recent discoveries regarding K2-18b, particularly the identification of potential biosignatures such as methane, carbon dioxide, and possibly dimethyl sulfide DMS, are paving the way for a transformative era in exoplanet research. As scientists continue to analyze and validate these findings, several key predictions can be made about the future of exoplanet exploration and our understanding of life beyond Earth.
1. Enhanced detection methods and technologies. The advent of powerful instruments like the James Webb Space Telescope JWST has already revolutionized our ability to study exoplanet atmospheres. Future missions will likely build on this technological foundation, incorporating even more sophisticated spectroscopic techniques and instruments capable of detecting a broader range of biosignatures. These advancements may include space-based observatories specifically designed to focus on exoplanet atmospheres, further enhancing our capacity to discern the chemical compositions and potential habitability of distant worlds. 2. Increased focus on Hycean worlds. The findings from K2-18b support the hypothesis that Hycean exoplanets, those with hydrogen-rich atmospheres and potential oceanic surfaces, may present some of the best candidates for hosting life. As more Hycean worlds are discovered, researchers will prioritize these environments in their search for biosignatures. This shift could lead to a more nuanced understanding of what constitutes a habitable environment, moving beyond the traditional focus on Earth-like rocky planets. 3. Refined criteria for biosignature detection. As the scientific community grapples with the complexities of interpreting atmospheric data, a more refined set of criteria for identifying biosignatures will emerge. Future research will likely emphasize the need for multiple lines of evidence before declaring the presence of life. For instance, the potential detection of DMS on K2-18b remains contentious, and ongoing investigations will aim to clarify whether this molecule can arise through abiotic processes. Such careful scrutiny will help establish a more rigorous framework for evaluating potential biosignatures across various exoplanets. 4. Collaboration across disciplines. The search for extraterrestrial life will increasingly require interdisciplinary collaboration, drawing on fields such as astrobiology, planetary science, chemistry, and even philosophy. As the implications of potential life beyond Earth become more profound, discussions around the ethical considerations of discovery will also gain prominence. Collaborative efforts may lead to the establishment of international guidelines for the exploration of exoplanets and the interpretation of biosignature data. 5. Public engagement and interest in astrobiology. The excitement surrounding discoveries like those on K2-18b can significantly influence public interest in astrobiology and space exploration. As more findings are shared with the public, educational initiatives will likely expand, fostering a greater understanding of the universe and humanity's place within it. Increased funding and support for space missions may follow, driven by public enthusiasm for the potential discovery of extraterrestrial life. 6. Potential for direct imaging of exoplanets. Future advancements in telescope technology may allow for direct imaging of exoplanets, enabling scientists to observe planetary features and even weather patterns. This capability would revolutionize our understanding of exoplanets, providing direct visual evidence of their atmospheres and surfaces. As we refine our techniques, we may even be able to capture images of biosignatures directly. 7. Discovery of new exoplanets and diverse environments. As survey missions continue to discover new exoplanets, we can expect a richer diversity of planetary types and environments to study. This expanding catalog will allow scientists to compare and contrast various conditions that might support life, enhancing our understanding of how life could arise in different contexts. The exploration of exoplanets in different stellar environments will also expand our knowledge of the parameters necessary for habitability. 8. Integration of artificial intelligence in data analysis. The sheer volume of data generated by observatories like the JWST will necessitate the use of artificial intelligence (AI) to analyze and interpret findings. AI can assist in identifying patterns and anomalies within complex datasets, streamlining the process of biosignature detection and atmospheric characterization. As machine learning techniques improve, they will become invaluable tools in exoplanet research. 9. Long-term missions and habitability studies. Future missions may focus not only on identifying biosignatures but also on studying the long-term habitability of exoplanets. This could involve monitoring atmospheric changes over time, assessing the stability of conditions conducive to life, and exploring the geological and chemical processes that shape these worlds. Such studies will provide a more comprehensive understanding of how life might evolve and thrive in different environments. Conclusion. The discoveries surrounding K2-18b are setting the stage for a new chapter in the exploration of exoplanets and the search for life beyond Earth. As research progresses, the scientific community will refine its methodologies and broaden its perspectives on habitability. While the presence of life on K2-18b remains uncertain, the journey to answer this question will undoubtedly lead to significant advancements in our understanding of the universe and our place within it. The ongoing exploration promises not only to enhance our knowledge of exoplanets but also to spark the imagination of generations to come.